This exam question comes from the Unit 3 exam paper for the A2 Physics. We're looking at an interesting question here where it wants us to work with radioactivity, it wants us to use our knowledge of half-life, etc. It starts out very simple. There's a nasty calculation later on, but otherwise we'll work our way through this, and it's relatively straightforward. I'll explain what is meant by the activity of a radioactive source. Well, I would say that activity is the number of nuclei that decay per second. It's a rate thing, okay? And then the unit for that is the becquerel, which I can't really spell, but we'll have a go. Becquerel. It's easier to remember, it's a BQ. Okay, that's an easy start. The half-life of radon the half-life of that is this. Radon is 3.3 times 10 to the 5. Determine the time it takes for the sample to decay to 20% of its initial activity. Now you have to do two things, which is a little bit of a trick within this question. So the first thing you need to do is you need to find from your data sheet the magic formula for half-life and decay constant, this lambda here, which is equal to ln2, which is a constant value effectively, over t to a half, which is the shorthand for half-life. So let's put some numbers in. So that's straight from the question, 3.3 times 10 to the 5, and that's going to equal 2.1 times 10 to the 6, and that's my decay constant, okay? So now we're going to use the much more familiar A equals A0 e to the minus lambda t. We've just found lambda, we're going to find t. It wants us to determine the time. So if I do some rearranging, I'd say that A over A0, that's a nice easy substitution there, equals e to the minus lambda t, still up there. If we log both sides of that, we can rearrange it as ln A over A0, keep that in brackets would be my advice, equals minus lambda t. So by logging it, we're getting rid of this e here. Bit of a trick that we're using. So 20% is 20 over 100. You could do 1 over 5 if you like, but because it's a ratio, the log will take care of it, however you choose to write it in. So that's going to be ln of 20, which is what I've got now, over 100 of whatever I started with, equals minus, I've just found my half-life, my decay constant, sorry, from up here for my half-life, 2.1 times 10 to the 6, and that's all going to times t. You can then solve it, so obviously you need to put that into your calculator. You then need to divide it by this, and that will give you a t value of 7.7 times 10 to the 5 seconds. Make sure you put the unit on it. You can convert it into days if you want to, but why would you and risk making a mistake and losing a mark? Discuss the extent to which alpha radiation particles are a risk to the human body. So I would say that alpha is highly ionizing, and I would mention that it causes cancer. It can do other things as well, but cancer is a nice simple example. Highly ionizing causing cancer, but it's only a risk if you ingest it. Stop for a second to check my spelling. Pretty sure that's not even how you spell ingested either. A risk if ingested because it is stopped by skin. So as long as it's on the outside, it poses no real risk. So here we go. So now we'll turn over for the next bit. This part of the question is quite complicated. There's lots of things to do, and you're going to spend a lot of time here pressing the buttons on your calculator. So we've got a nuclear decay equation up here at the top, and the radium is turning into radon, and we've got the data here to go with it. It's actually very easy, but there's lots of easy things to do, making it quite a complicated thing to do overall. So the first thing we do is we'll work out, I like to do it like this, so we'll work out what's on the left-hand side, and then we'll minus what's on the right-hand side. So what's on the left-hand side? So we've got the radon, which is 226.0254110, and that's coming from there. But that is the atomic mass. So we need to take away the mass of those 88 electrons, which are included in here, but not included in this calculation here. So we'll then take away 88 times the mass of the electron. And if you do that, you find out that your answer is 225.9777098. For now, I'm working to a ridiculously large number of decimal places. On the right-hand side, I've got this guy, the radon. We've got 222.017578. Again, I'm going to take away the 86 electrons. That's 86 times 0.00. It's all going to go in the calculator in a minute. That's going to be fun. 549. Okay, and I've also got the helium, which is 4.002603 minus the 2 electrons that's got. Okay, stick them in brackets if you like to help you organise and visualise what's going on. And once that's all plugged into your calculator, that'll pull out with 225.97. I'll try and write it down right for you. 1869. That's in U and that's in U. Okay, atomic mass units. We'll slide it up. So what's the difference? So it's going to be the left-hand side minus the right-hand side. So it's going to be that minus that. And if you complete that calculation, you will get, he says, 5.229 times 10 to the minus 3. At this point, I'm starting to shed some decimal places because I'm getting lazy. Put your U on the end to help you out with that. Okay, now this is an energy question. So what it wants us to do is it wants us to calculate the energy released. Well, that's the mass lost. So the next thing I'm going to do is turn it into an energy. So using your conversion figures that you are given here, 1U is equal to 931 MeV. Let's turn this from a mass into an energy loss. So I'm going to say energy equals 5.229 times 10 to the minus 3U times 931. And that's going to give me a value of 4.868. I'm going to bring them all back in. 199 MeV. And then we need to turn it into joules, because I like joules a little bit more, if I'm honest. So there's a conversion factor, and this is written on the front of your... no, it isn't. This is something that you'll need to know. So we need to times it by the charge on an electron. But remembering, of course, it's MeV, so it's millions. So what I would then advocate doing is timesing it by 1.6 times 10 to the minus 13. So that's times 10 to the minus 19. But because it's MeV, it's a million times bigger. So it's times 10 to the 13. And that's going to give us 7.7891 times 10 to the minus 13 joules. And I'm going to have a quick check. Is that a tiny number? Yes, good, because it should be. It's always going to be a small value for joules. Go back to the top question up here again. It actually wants me to work out what the speed of a nucleus is, the speed of this helium, if it's got 98%. So I'm now going to find 98% of this. So I'm going to times it by 0.98. And that's going to give me... I've managed to put that down somewhere. One moment, please. That's going to give me 7.633 joules. So that's, times 10 to the minus 13 joules. So that's 98% of the energy released, which is turned into kinetic energy. Kinetic energy is equal to a half mv squared, therefore V is equal to 2 times the kinetic energy over the mass, square rooted. Numbers are going in again, surprisingly here. So V is equal to 2 times that 7.633 times 10 to the minus 13 all over 4. And this is the mass of the alpha particle, which is effectively 4u. It'll be close enough in this case that we can do that. So 4 times u off your data sheet as 1.66 times 10 to the minus 27, all square rooted. And when your calculator is finally finished with that, it'll be 1.52 times 10 to the 7 meters per second. Okay, lots of button pushing on your calculator. Lots of simple, but lots that are complicated by the sheer number of those simple steps you needed to do. Great job, good work. Go and enjoy another video.